We will start with erratic motion. Let's put our title erratic motion. So we will start with S and T graph. Let's write it S and T graph, which is time and position. S and T graph, which is position and time graph. Let's draw S and T graph. So let's say we have time here and we have position on this coordinate, and we know that let's say we have a time and position graph is like parabolic, like some kind of this graph. And let's change the colors, and we can divide it into T1, T2, T3. At T1, let's say at T1 our position in this point, at T2 position of this point, and T3 we know that we can easily read these graphs, right? Here when we correspond this this kind of graph, we need to take to like tangent. Let's say our v0, which is initial velocity, is ds over dt, right? ds over dt is the slope of this graph with a time is equal to 0. When you take this guy, time is equal to 0. If I want to take this time t1, the velocity, I need to take these guys derivative with respect to position, with respect to time, position with respect to time, where when time is equal to t1, and same thing on this slope and on this slope. Let's say, okay, let's take this guy, ds over dt at t is equal to t3 is gonna give us the velocity at 3. Okay, velocity at time 3. So let's give definition, and we can state it. So plots of position is versus time can be used to find v. Sorry, let's take this guy here. Find velocity, which is v, let's say, versus time. Okay, so plot of s and t can be used to find the velocity and time curves, time velocity versus time curves. So finding the slope of the line, tangent to the motion curve at any point is the velocity at that point. So in another word, we can state this one is ds over dt at 3, time is equal to 3 is giving us velocity at 3, and time is equal to 0 is going to give us velocity of 0, the initial velocity. So this is the basically definition of this kind of graph. Let me write it. Therefore, okay, it's mixed. Let's write it here. Therefore, the velocity versus time graph can be constructed by finding the slope of at various point along the s versus the position versus time graph s. So we can right now we can construct our velocity and time graph by looking this guy, this position and time graph. Let's construct our velocity versus time graph. This is time and velocity. So it's gonna be at the beginning the velocity is like the tangent line is very smooth, right? Is high. So then it gets almost the tangent of this curve is getting 0. Then after that maybe it's gonna turn back. So we can draw this line as, let me draw with the red one, and it may be like, we assume that it's gonna be like this, right? It comes to 0, then it turns back, and we can state also here as t1, then it turns to, like, let's say we have here t3. I'm just assuming, like, let's say here is t3 because it's almost this is t2, almost 0, right? So it's on the dome of, let's say it's almost dome of this one, so it's very close, so I just assume it's like t2. So here is the t1. So we draw velocity versus time graph according to above, which is position and time graph. And let's continue like how we are approaching more. So now let's cover the velocity versus, if we have velocity versus time graph, what we are gonna do is basically the same thing as the position and time graph. So let's think we have a time and versus velocity graph, and let's say we have like this kind of motion, the velocity curve we have, or like let me go back, is like here, then it's turning back. Okay, so and let's say we have here velocity 1 at t1 and velocity 2 at t2, and over here is t3. So we have velocity 0 here, velocity of 1 at time 1, 2, 3. We have all these guys, and then we know that if we take this curve, this tangent line, we are gonna find the acceleration. So acceleration 1 is gonna be dv over dt at time, t1. T is equal to t1. When we take this derivative, we are gonna find here acceleration 1 value. Then if we take here, we are gonna find acceleration 2 value and 3 value. So if we take the derivatives of on this graph, we will find it our acceleration versus time graph. Let's write it again. Plots of velocity versus time graph. Oh, not already right. Plots can be used to find acceleration versus time curves. Finding the slope of the line tangent to the velocity curve at any point is the acceleration at that point, right? Or it is basically dv dt at time whatever we chose. And continue, therefore A versus T graph can be constructed by finding the slope of various points along the velocity versus time graph. Okay. What else? Also the distance traveled of the particle is the area under the velocity and time graph during the time difference, which is delta t, right? So if we take integral of v dt, so the area under these guys is gonna give us the distance, the total distance. Okay, first of all, let's construct it A and T graph with respect to this guy. Okay. So let's do red one. So let's say it start to increase, then after that decrease the velocity. So it's gonna be first is coming like this curve, then bell shape, then after that it goes down. Some kind of this one, you know, like not exactly, but I am just assuming that we are gonna solve questions. So A0 here, sorry. A0 is 0, let's say. There is constant velocity first. Then after that, we are gonna go through as A1, A2, A3, like a T1, T2, and a T3. So we are gonna find A1, A2, and A3 in these points, and which corresponds to velocity and time graph. Let's continue at again our time graph, which is the last one, is a acceleration versus time graph. Let's define this one as well. So this is basically our again physics 1 class. We just reminding this physics 1 class, and let's draw again a graph of a and t t and a, and let's assume again like this curve, acceleration versus time graph. So the acceleration and change the curves with respect to time is not constant, and in this term we need to go backwards. So is acceleration versus the time. We cannot take anymore the differential because there's no other dimension for the physical dimension with respect to this acceleration derivation. So that's why we need to take what the, if we have, like let's say after t1 we can find the velocity or position. So the velocity is the under this curve, area of under this curve, which is we can define as delta v, which is the change of velocity, not initial, not exactly the point velocity, is the velocity change between 0 to t1, right? 0 to t1, and what we are gonna do, a dt, if we have the function of this curve and we take the t1 under this curve area, is gonna give us the velocity change. Okay, let's continue to define. Given the a versus t graph or curve, let's say curve. Let me put this guy here, so it's gonna be in neat. It can be neat. Okay. The change in velocity, which is delta v, right? So let's say delta v, during a time, during a certain time period, is the area under the AT curve, a versus t curve, area acceleration versus time curve, is gonna give us the change of velocity. So we can construct a velocity versus time graph from an a versus acceleration versus time graph. How? If we know the initial velocity of the particle. So only condition is we need to know the initial velocity, then after that we can construct velocity versus time graph, because this a and t graph is only giving us the change of velocity. So let's assume we have an acceleration and we know that the initial velocity. So let's say we have these guys like is more than this parabola, and we can say this one is velocity of 0, which is initial velocity, and we will see at time 1 is velocity 1, which is between these guys, is gonna give us the from this curve under area. We will find v0 plus delta b, this integral, and we can construct velocity and time. So time versus graphs is done here. Let's pass to, if we use the position, like velocity and position and acceleration and position, what we are gonna do. Our next case is acceleration versus position graph. So let's draw an acceleration versus position graph. This is position, this is acceleration. Okay, so let's draw again a curve, kind of this. Okay, so acceleration changing by position. All right, turn this one, and then let's say at position, initial position, and later on S1. Okay, here the initial position, let's say 0. 0 is if we have an initial position, and then if we assume the initial acceleration is a 0, then the change, because we know that this guy is the velocity term, right? So is not velocity term basically, but the integral, we need to convert it to velocity, this term. So if we take the integral of this one, a ds, from 0 to s1, okay, so because we need to take the integral of position, what it need to be is gonna be 1 over 2 velocity, the first velocity at time 1, or the position 1, sorry, minus initial velocity square, both of them square. Why? So right now let's define first of all and then after that why we change this integral in this form. Let's see. Okay, I will remind you, a more complex case is presented by A versus S. A more complex case is presented by, acceleration versus position graph, because the area under the A versus S area, acceleration versus position curve represent the change in velocity. But when we take the velocity, is not pure velocity, is not v1 minus v0, because we know that from our first class is ADC ds, not DC, ADS is equal to integral of v dv, right? We have this formula So if we take from S0 to S and V0 to V, we need to, like, if we take ADS integral, we need to find VdV, which is VdV is 1 over 2 V1 square minus V0 square. That's why I wrote it in this form. Okay, that's right now. If this one is clear, let's jump to how we can proceed it. This equation can be solved for V1, which is velocity 1, right? Allowing us to solve for the velocity at a point. By doing this repeatedly, we can create a plot of velocity versus position. So if we do this guy repeatedly to make it the integral, then we can plot our velocity versus position graph, S and velocity, by looking this way. Okay, let's again draw a line more hyperbolically like this guy. Okay, and we will say, okay, we know that our initial velocity, and at position S1, let's say we have here, we can define our velocity of one at position S1, and we can construct our velocity and position graph. We can all solve examples and then we can understand better. The last one is the velocity and S, and then we are gonna do, right? Lastly, we will cover velocity versus position graph. Velocity versus position graph. Okay. Again, let's draw one velocity and position graph draft of this guy. Let's say we have a position here and velocity here, and let's draw again v0, which is the initial velocity if we have, and if we take these guys as s1, if we take the tangential of this point, and if we take the derivative, which is dv ds, what is gonna give us? The acceleration, and let's say a1 acceleration. Then we can construct it here. Then t versus a graph with respect to velocity and s graph, right? So let's say here again, if we write it, if we draw a graph of acceleration versus not time is position, so it's gonna be a0, the initial acceleration, and s1 we can cover here, and a, if we convert it to a, is gonna be v dv ds, right? Because we know that a is ds, ads is v dv, so we can say acceleration at this point is v dv So we can convert it, this A and S graph again, to velocity and position graph. Let's define with verbally, and we can finish up this erratic version. Another complex case is presented. Right? Is velocity and acceleration, velocity and position graph presented by the velocity versus position graph by reading the velocity of v at a point on the curve and multiplying it by the slope of the curve, which is dvds, at the same position or same point, we can obtain the acceleration at that point. So is the verbal explicitly explained by this case, and we know that a PDVS, as we know, and thus also we can construct an acceleration versus position plot from velocity versus position curve. So therefore we are done for the erratic motion. Let's solve the examples and we will understand better. Okay, let's start with one example. Example 1. Our first example is the position and time graph of a sport car. Moving along a straight line that the velocity and time graph and acceleration and time graph over the time interval. Let's change it like this. In plot, say plot the velocity and time graph and acceleration and time graph over the time interval shown, which is, let's draw a position and time graph. This is time, which is in second, the unit is second, and the position is in meter. Okay, and our curve of this position and time graph is parabola. And okay, let's draw. The top point is in 10 seconds which corresponds to 225 meters. 225 meters. And in 5 minutes also given, which is in 5 minutes it corresponds to 75 meters. So this curve corresponds to in 5 minutes 75 meters and 10 minutes 225 meters. Alright, let's try to solve this question. Of course, before we solve this one, we need to know how this curve behaves, or the function of this curve. S from 0 to 5 behaves like 3t square, and from 5 to 10 the position function is 30t minus 75. So let's do in two parts, which is 0 to the time is between 0 to 5. It is, we can say v 0 to 5 is the derivative of this function. So ds over dt, right, which is if I take 3t square d over dt, 3t square derivatives, which is 6t, and v from 5 to 10 is again d over dt. It is 30t minus 75, which is when we take the derivative we can have 30. So both of them meter per second, let's say meter per second. So we can understand here that 6 multiplied t is a linear, its growth increased linearly with respect to time velocity from between 0 to 5, and between 5 to 10 is a constant velocity which is 30. So we can draw easily so which is t versus v, which is meter per second and time is in seconds. When we draw our curve is a linear curve which corresponds to 30 from 0 to 5, right? 5 multiplied 6 is 30, so it's linear. Then after that is constant from 5 to 10. So if we want to use this one and then find the acceleration term, we know that a is dv dt, a 0 to 5 is dv dt, which is d over dt 6t, which is constant 6 meter per second square. But a from 5 to 10, again dv dt, which is d over dt 30, which is 0. So if we want to draw our acceleration versus time graph, let's draw here. time in again seconds, acceleration is in meter per second square. So okay, and then if we want to draw, it's gonna be constant from 0 to 5, then after that 0 from 5 to 10. 5, this is 5, this is 10, and this is 6. So we draw velocity and time graph and acceleration and time graph with respect to given position and time curve. Let's solve another example. Example 2. It is the given right now the velocity with respect to time graph is given. Find the acceleration and time graph average speed and distance traveled for the first 50 seconds of travel. 50 seconds of travel. So we are gonna find the velocity and acceleration time graph, then average speed and distance traveled in 50 minutes. The question graph is given as these guys. So it's time, which is again seconds, and velocity term here, which is meter per second. And if we want to draw our graph is a straight line, then after that is constant, going constant. So here is 30, here is 50 seconds, and here is 12 meter per second. Okay. So let's start to solve. Here, let's plug here and then start to solve. We know that from 0 to 30, between 0 30, A is given by dv dt. So as we can predict, dv dt is the tangential of this curve. So it's the aim, you know, the tangent line of this guy. So if we know that if it is like a right angle triangles, we can do this one as 12 over 30 if there is just like a straight line. So it's gonna be 12 over 30. It's gonna give us the acceleration, which is 0.4 meter per second square. 0.4 meter per second square. And from 30 to 50, acceleration is again the slope of velocity with respect to time, which is horizontal line, so it's 0, right? So when you take the derivative, it's gonna be 0, as obvious. Then we can draw the first question answer, which is time versus acceleration, which is this 1 meter per second square, and time is in seconds. So it's gonna be between 0 to 30 is 0.4 meter per second square. Then after that is 0 till 50, and this is 30, and this one is 0.4. So we draw our acceleration versus time graph. What else we need to know? We need to know the average speed. So first of all, before average speed, we need to know the distance traveled. So when we divide 50, we will find velocity, right? So let's do it again here. Let's do it with blue. So delta S between 0 to 30 is the integral of velocity and dt from 0 to 30, right? So velocity is 0. It's a linear, and so we can basically directly say at, which is 0.4. The acceleration multiplied time is gonna give us the velocity curve, which is linear, as I said. So dt from 0 to 30 is gonna give us the total distance traveled between 0 to 30. When we take the integral, is 1 over 2 0.4 t square from 0 to 30. We need to add this one, and when we substitute this 30 and 0 here, 0 is gone, here is gone, 0. 30 square multiply 0.2 is gonna be 180 meters is gonna be our answer, right? And from delta S from 30 to 50, again we need to take the integral of from boundary 30 to 50 dv dt. We know that velocity is constant here, which is 12, so it's not depends on the acceleration, so we just need to write 12 dt, which is 12t between 30 to 50, which is given us 50 minus 30 is gonna be 20 multiplied by 12 is gonna be 240 meter distance traveled. The total of delta S, which is 0 to 50, is gonna be 180 plus 240, which is 420 meters, which is total distance traveled between 0 to 50. And if we want to find the average velocity, v average, what do we need to do? We need to divide delta S by delta t, which is 420 meters over, which is delta t is 50 seconds, right? So we will have 8.4 meter per second of average speed this car has it. Let's do the last example for this week, example 3. Again, we have velocity versus time graph is shown below. We need to find the acceleration. Find the acceleration and time graph. Average speed again. Average speed and distance traveled for the from 0 to 48 second interval. Okay, we are gonna find again average speed AT graph. Basically is the similar, but right now let's see the first graph, then how we are gonna approach. Let's see, here's the time, here is the velocity again, which is meter per second again, which is second, this one again, and our curve is gonna be look like a triangle. Then after that, put this into here. Okay, so in the top point, when we go through down, is 30 seconds, and the last point is 48 seconds. So it's not equilateral triangle, and we have the top point of velocity is 6 meters per second, and the question is given the velocity curve. The first one is 1/5 t, 1/5 multiplied by time. Then the other one is the velocity curve is minus 1/3 t minus 48. T minus 48 is given both sides. Curve. Okay, let's put here so we can see and then observe and then do question easily. From 0 to time 30, we know that we can define the acceleration term by taking the derivative of the velocity. From 0 to 30 is 1/5 t, which is a constant acceleration given, which is 1/5 or 0.2 meter per second square, right? 0.2 meter per second square. And from 30 to 48 seconds, our acceleration is again d/dt, the first derivative of the given function, which is minus 1/3 t minus 48, so is given minus 1/3, right? And we can say it is minus 0.333 meter per second square. So let's draw our acceleration term. We know that from acceleration versus time graph, time and acceleration. So both of them is constant. So like we can define where from 0 to 30 is gonna be from 0 to. So it's like this guy. Let's say here is the 30. Then after that, from 30 to 48 is gonna be minus 0 point, right? Here. So here is 0 0.2, 0 0.2, here is 0 0.333, but it's a minus side. Okay, let's put the unit meter per second square. Here the time is seconds. So all right, after we add these terms as well, let's jump to find our total distance between 0 to 30. From 0 to 30, as we said, is the vdt between 0 to 30, vdt, which is the velocity is already given by 1 over 5t. The velocity is 1 over 5t, so it's gonna be 1 over 5, 1 over 2 t square, the integral from 0 to 30 we need to do, right? If we take the integral of this guy, so it's gonna be 90 meters. Shortly, we are doing delta S from 30 to 48 meter is again integral of 30 to 48 meter of velocity term dt, which is velocity of this guy. It was minus 1 over 3 t minus 48, so I can say it's the minus 1 over 3 is outside, so in the parentheses 1 over 2 t square, right, minus 48t is given. The integral from 30 to 48. When we substitute this term, is gonna give us 54 meter, is equal to 54 meter. So total distance traveled is 90 plus 54, which is 144 meter, 144 meter, and the average velocity is 144 meter over 48 seconds, which is given 3 meter per second. So we solved this question as well. Thank you very much for listening.